This is probably going to be uh, our last or second to last, we're not sure yet, meeting of this year. And we have 2 more weeks of school, I think. But because it's review week, we are close to the end. And we are, yeah, going to start lightly. And we're going to also talk about things to expect for next semester and our plans for the next after our unit so far.
All right. So let's begin with our physics news. Our physics news is a little bit from 2008 for electricity and magnetism. We're going to be discussing the Large Hadron Collider. It's a 27-kilometer long tunnel. It's like somewhere between like the city of Switzerland, Geneva in Switzerland, and between like France, right? And so it photographs collisions of subatomic particles, like protons, right? They're called hadrons. Is the category, the super category. And that can include like protons, neutrons, mesons. We're going to talk about all about that in the particle physics unit. Let's look at this link here. This is like a tour of the LHC. It takes a bit to load. All right. So here's the Large Hadron Collider. And it gives you some information over here on the side. So you can look it through the facility a little bit. It's a very big scientific facility. Here they're going to show you, this is Atlas. This is one of the places where they take a photograph of the collision. And they have compact muon solenoid. It's a very complicated scientific facility. They have like lots of stuff in here. And this is Alice. This is another photographing area. And here, I think they get photographing here the collision. This is one of the places where they take a picture, if I'm not mistaken. This is the tunnel. So it's 27 kilometers long. So if you look at the wall over here, this looks like nearly straight, but it is a circle. It's really, really big, 27 kilometers around. And on the left, you see like all this piping right here. That's where all the magnets are in the facility of the Large Hadron Collider. And so the magnets, the strong magnets, electromagnets, are allowing the collision of the particles to occur, right? Because like protons, they're like charges, right? So the protons actually like repel, right? But the collision is actually able to occur due to these magnets. So there's like a few magnets. I think they're like in the gray sections. They're either in the blue or the gray sections. And so this is a physics photo. This is the photo of the proton collision. This is actually a really cool photo, guys. This is one of my favorite physics photos. And so here you can see two protons actually colliding. And this is actually depicting E equals mc squared, because these two protons are coming in like a lot of huge energy and colliding, right? And so you can see all this new mass that's being formed in the collision, right? So you might think, well, this breaks the law of conservation of mass, but it's actually the law of conservation of energy and E equals to mc squared, which is depicted in this collision. And this is a photograph taken from the LHC, the Large Hadron Collider. Right, I will continue with electrostatics. So there's a few key concepts in electrostatics, like charge. So here's a few facts. Charge is a fundamental property of matter, like mass, and all matter is composed of like these charges, right? Like protons and electrons, you've definitely heard in all your science classes that all matter has charges. And charge, it's really hard to come up with like a specific definition. One way we can define it is we can say that a charge describes the electric field that a particle or object can form a certain radius away. We're going to go more into depth into that. And it has units of coulombs, which it seems arbitrary for now. It's 1.6 times 10 to the 19th electron charge. There's actually a very good reason why it is that way, which you might explain in the future. There's two properties of charge. We have quantization of charge and conservation of charge. Quantization tells you that all charges are found in multiples of the electron charge, right? That's an experimental fact. It's a purely experimental observation. That's how we like observe charge in the universe, right? Now you can think about like quarks, right? If you like how like proton or a neutron, those are like broken into like 1/3 charge, but they're always like bounded in like threes, in trios, right? So even in the case of quarks, you find that everything's still in multiples of the electron charge because they're always bounded in threes. So experimentally, that is a fact. There's also conservation of charge. Charge cannot be created or destroyed. Like say you have like a rod and a fur, right? And so you rub like the fur and the rod. You rub the fur against the rod. And so you're actually taking some electrons from the rod to the fur. And so what's happening is that the net charge is still preserved, right? The rod is just slightly positive and the fur is slightly negative, but the charge is still conserved. So that's conservation of charge. And so now we're going to talk about some visuals about some of the electric fields that are being created by these charges, right? So there's a lot of nice visuals here. You can see just if we have like just a positive charge in space, that's the electric field at some points away. And over here, you can see the electric field for negative charge, right? So for the positive charge, you have like a divergence here, right? And that's going like outwards. And for the negative charge, the electric field is going inward. So that's a key concept. Over here at the bottom, you can see the pairs, right? You can see dipoles here, actually. You have positive charge and negative charge and the field between them, and then positive and positive charge and the electric field between them. We're going to go more into depth into that. Here's a visual. Here's a visual. This is in 3 dimensions. You probably haven't seen this one before. This is a really cool visual. This shows the 3-dimensional version. So you can also go like out of the plane and into the plane. And so these are showing like the field lines of the charges. You can like edit the charges. So this is currently positive and negative charges. And I think I'm currently not able to edit those charges. Or actually, never mind. The Zoom window is blocking that. So we can make them like charges, right? Now here's the electric field if we make those two the same charges. They're both +2 now. And so you can see that the geometry is different for the vector field here. And so this is all because of the Coulomb's law. And it looks similar to like the law of gravitation. Even though gravitation is not actually a force, as Boang was covering a few club meetings ago, we can kind of use the law of gravitation as an analog to this, the Coulomb's law. And so this is the scalar form of Coulomb's law. Sometimes you like to write it in vector form, right? Because if you have 2 charges, so this is the vector. Let's explain the scalar form quickly. It tells you that the electromagnetic force is equal to K, which is a constant, times the product of the 2 charges divided by the square of the radius, right? So if you have like 2 opposite charges, like a positive charge and negative charge, then the force is negative, right? Because K and R have to be positive. So the force must be negative in that case, and that's the positive and negative charge is attracting, right? Versus if they're both positive charges, then you're going to have it, right? So scalar form, but sometimes when we're doing like problem solving with these, we like to use the vector form. That's a bit more formalized electromagnetism. I might pull up like a whiteboard and quickly show it. We have a positive charge here. That's a positive charge. And then we can draw the negative charge down here. And so this is like charge 1. You can call this one charge 2. And you have like a radial vector, R12, between them, right? But you also need this like unit vector. There's like a unit vector here. I haven't drawn this very well, but there's a unit vector. You can draw one R hat right here. So this is more for like problem solving with like charges, but you'll have like unit vector, for example. And then this helps you to work out like a system of charges, for example. But we're not going to go as much in depth into that. That's a mathematical tool. So we have Coulomb's law here. And we also have the electric field, which is essentially, you can think about like gravitational field, right? Where you were taking the force and you were dividing out the mass, and that creates the gravitational field at like all points around a certain mass. And in this case, you have the electric field, E. And so that's where you divide out one of the charges and you look at the field around a certain charge. And when you take this vector here, it becomes a vector field, which is very special. And that's where you can look at like the ideas that we were covering before, how like around like a charge you have positive charge, you have like the divergence. And then in the negative charge, it's going like inward, right? So it's a similar idea there. And so now we're going to look at a molecular workbench demonstration of Coulomb's law. So here's the molecular workbench demonstration. And so this is a very cool demonstration. We're going to play a small game with Coulomb's law here. And so here's how the game works. This is a positive charge over here. There's a positive charge here, positive charge, and negative charge. And what we're going to do is we're going to take this like white circle, and we have to kind of get it to this target area right here. So I practiced this a few times before the meeting started. I'll see how this goes. And so we can run it, and that's going to start the timer here. And so we have the positive charge first. So we should try to use the negative charge.
I think it's not showing up on the screen share.
Thank you for telling me that, Alan. I will see if I can screen share that. Sorry, I have to switch like screen shares or something. But okay, now is it visible?
Yep.
Yeah.
All right, thank you. Let's reset that. Here's the game. You have a white circle over here. You have positive charge here, positive charge here, positive, positive, and there's a negative at the top right. And so we have to try to get this white circle into the target area by changing between the positive and negative charge. So it's a fun little game that applies Coulomb's law and the principles, right? That the like charges will repel and the opposite charges will attract. So let's look into that. We can run it. That will start the timer. So I ran it. And let's start with the negative charge, right? Because these two charges will attract. So now this charge is going to start moving toward that charge. And now we just send this charge away from that charge. It'll be stuck here, right? So now we would change to the positive charge. And I'll change back to negative for attraction here. And this repeats for a little bit. All right, so now we're over here. Now we have a negative charge at the top right here. So once we change it to the positive charge, you can see that they attract, and then we can use the negative charge here because negative and negative will repel one another right here. And so we'll be able to make it to the target area and complete the game. And so that's using Coulomb's law to play the maze game. You guys can access this, I think, from here. You can go to like the electrostatics. Mine's running a bit slow right now here. You can go to the electrostatics, and then you can go to like these different activities. You can try this out if you get like molecular workbench. I believe we have like the download instructions at the beginning for molecular workbench, but we can show those again sometime later. But there's a lot of cool resources in molecular workbench, like this maze game. Anyways, so let's switch back to the presentation. So here we have Coulomb's law, as we have demonstrated. So next we're going to go into the Maxwell's equations. We're not going to go very deep because these are very mathematically heavy, but we're going to cover some fundamentals here. It's the idea of flux, right? Flux is simply the way that a field will hit a certain geometry, right? So for field, we have electric field and magnetic field. And for geometry, you can think of it like either like in a path, like some kind of like contour or like a path, like a circle, right? Or like a box, for example, like a rectangle, sorry. A rectangle, for example, or a circular path, one of those kinds of path. You can think of like a circle, right? A surface, sorry, a surface. You can think of a surface, like a certain surface area, right? Like you guys learned this in like geometry. You can have like a sphere and you can have like some kind of surface area on that sphere, for example. Or you can have just like a straight up like a volume, right? A complete volume. So these are Maxwell's equations. There's like a joke of let there be light, and God said let there be light after he said these 4 equations, right? So there are the 4 equations. and they're very fundamental to electromagnetism in general. This first law is Gauss's law of electricity right here. And it tells you that the electric flux over a certain area, right? So we're talking about, you can have like electric or magnetic, and then you can have like path, surface, or volume. So the electric flux over like a surface or an area is equal to the charge enclosed divided by epsilon naught. Epsilon naught is just a constant for now, you can think of that. That is Gauss's law of electricity, which is, it's very useful for finding like charges over the surface of a conductor, the charge distribution there, for example, right? This next law is Gauss's law of magnetism. And Gauss's law of magnetism is very useful in that it tells us that you can't have the magnetic monopoles, right? Whenever you cut a magnet into two, you always get another magnet. And this law kind of enforces that idea. And so magnets always occur in dipoles, right? You have the North Pole and the South Pole. Although we're going to cover more about magnetism in the future. This next law is one of my favorite laws in electromagnetism. It's Faraday's law. Faraday's law is the electric flux. Like this one's, you can see like the ds over there. That means that it's over a path. So it tells you that the electric flux is the change in the magnetic flux with the electric is the change in the magnetic flux with respect to time, right? And so that's telling you about Faraday's law here. So this is very useful if you're having like, you can think of like a magnet, and a magnet will slow down inside a copper pipe. That's Faraday's law, how the magnet can slow down in like a copper pipe. And I think that there's a few cool demonstrations about that on YouTube because of like the cross section of that pipe. Now this last equation is very fundamental. This last one is Ampere's law. And it's usually, you can see like there's this component here, mu naught epsilon naught component, and then you have another component, mu naught times the current enclosed. And so I've seen like the equation used in terms of each of these components, like integral b dot ds is equal to mu naught times the current enclosed. And I've seen like integral b dot ds is equal to just this left term right here. So it's usually used like separately. It's usually not used like together. But it's useful for solving like magnetic fields in different kinds of geometries. So the one really cool result from Maxwell's equations is the speed of light and electromagnetic waves, right? So this last equation is actually a wave equation. And it tells you that 1 over v squared is equal to mu naught times epsilon naught. And it's a little bit hard to recognize. You learn this like a few years maybe down the line in college, but this is a key equation that we can actually get from the Ampere's law. And using that, you can solve using some simple algebra, right? You can solve for the velocity, which is the speed of light, which is square root 1 over mu naught times epsilon naught. Maxwell came up with this like in the 1800s. You can see the electromagnetic wave here. And so it's made of the electric field and the magnetic field, and they're perpendicular to one another. The electric field is propagating up and down in the y direction, and the magnetic field is propagating in the z direction, back and forth. And the direction of the propagation of wave is in the x direction. You can kind of see the wave propagating here. Next, we have the key concept of Lorentz force. So this looks intimidating. It's just to introduce the quantum computing, which is the next slide. It's simply derived from the, so this is two components, right? This Q times E. Q times E is electric force. So you can also see this visual here. Q times E is the electric force here. And this derives from back here, we were talking about Coulomb's law, right? How if you divide out the charge, you get E. So if you get like Q times E, you get the force again, right? In the vector form. So here you have Q times E, which is the electric force component. And then QV cross B is a magnetic force component. So the sum of these two components will create the electromagnetic force. This is a key concept in electromagnetism. It is the Lorentz force. Now we're going to talk about how does electromagnetism apply to quantum computing. So there's some examples in terms of electron spin, photon polarization. We talked about that in our SAT physics and optics videos, the photon polarization. And there's also the superconductors. So this is some information about quantum computing. So computers use like bits, 0 and 1, those are classical bits, right? But quantum computers apply the idea of superposition. And you can write it as A times 0 state plus B times the 1 state. So subatomic particles, in colleges, right, in some universities, they use like the outermost electron of phosphorus actually as qubit. And so they rely on the property of spin, that the electron can actually align with the magnetic field. Spin doesn't mean that it's actually spinning. Spin is more of the idea that it has angular momentum. If you're familiar with like some AD Physics 1, for example, I think they might cover it there. But if you have some experience with physics and you know about like the angular momentum, that's the idea of spin. And so if the electron is aligned with the magnetic field, that is low energy state, right? But it takes work to put it in the high energy state. So you can think about like the needle of compass. If you can take some force, right? It takes some force. It's normally in like the normal state, or like facing north, for example. But if you want to turn it like south, you have to take some work to do that. And so the electron can exist between spin up and spin down, but the active measurement will force it into a state, into one of the spin up or spin down states, right? So low energy is the spin down state, and then high energy is the spin up state. And so there's also probability densities involved. There's a little bit of mathematics involved. So this is the comparison between a classical bit and a qubit. So in classical bit, there's two numbers right here, right? So it's one of the 4 possible states with 2 bits, right? And if I wanted to determine the state of the system, you would have to give me 2 numbers to do that. On the right here, we have the example of the qubit, the quantum bit right here. And here you can see there's actually 4 quantum states from these 2 qubits, and you would actually need 4 numbers to determine the configuration of this system.
So because the qubits are in an entangled state, we need to measure them multiple times to make sure that we get the accurate result. And this really relates to the double slit experiment that we did. If you remember, there's a probability of each position, and if we measure it multiple times, we will get the result that we expected. And this relates to how we write the code in quantum computing. It's very different than traditional code. We want our code run so that it gets the result that we want, because it doesn't work each time. If we keep measuring it a lot of times statistically, like you flip a coin, if you flip a lot, you will approach 50% for heads and tails. And if we can go back a little bit to the 3 types of quantum computing, like the previous slide, I think, or slide 12. Yeah, so there are 3 types. These are 3 examples here, and for electrons, it's relatively new, and it's what Andrew talked about yesterday in his lecture. They use electrons in the silicon chips. They create 2 electrons in entangled state, and thus they use this microscopic level quantum state to do quantum computing. But it's very new, and there are other 2 types. Photon polarization, as Rohan said, it's what we talked about in our SAT2 video, but we didn't go into the application in quantum computing. It's basically light has polarizations, and it's a quantum state that we can use. And the third one is superconductors. So there's a misconception about quantum only happens in the physical level, like quantum states, but it can also apply to large objects if we put them in superconducting state. How we achieve that is placing it in very low temperature, close to absolute 0 or and in vacuum. So we can please do slide 16. And so this is a very cool object, and so we will learn about what it does exactly in a moment. But on the top left, that's a illustration of what it is. It's closely related to the ENM we talked about today, and It's basically a current loop. So the current is flowing to the right, as you can see in the middle picture, and there's a loop in the middle. And usually if the current was split, it goes into circuit, but we're just going to explain what it does. So the current split into I over 2 on top and bottom. But right now, if we apply a magnetic field in the middle, it will create a current because uh, I think it's yeah, right. It's one of the laws we talked about here today, I think. So we didn't go into the right-hand rule, but we can deduct from the uh, direction of the field. Um, if we have, for example, a field upward, the currents will formalize in a counterclock direction, and it will go against the currents in the upper half of the loop and amplify in the lower half. And here, because this object is in a quantum state, because we make it a superconductor, and we will have observe this graph on the right, where J is the small current that is that is formed by the flux. Interesting, if we have a normal object, the current will go all the way up as the flux increase. Uh, also, by flux I mean uh, it is the magnetic field um, times the area of the middle, but you can basically understand it as magnetic field for now. So as the field increase, it alternates. So when the flux increased to half the quantum level, as Rohan talked about, the field is quantumized as well as the magnetic field. So when it goes to half the quantum level, it will reverse because it wants to lower the energy. If you keep increasing the currents, the energy will also increase. But because it's in quantum state, it can reverse the current because it can, because um, the currents, it's moving both counterclockwise and clockwise. It's the entangled state that we went through in our previous unit. So that's why it's in quantum state. Basically, it can reverse its direction. And so it reverses, and the total currents IC, you can see it will go up and down because it's keep reversing in the lower half as well as the bottom half. So this is a graph of a upper half. It's decreasing first, and then because it's reversed, it increases. And next slide, please.
I think we are out of time for now. So I think next time we're going to continue with the quantum computers a little bit more.
Yep. Perfect. And thanks, everyone.
Thank you, everyone. I hope you learned something.
Thanks, guys. You gave my Physics C kids a head start.
Thank you. Bye.
Thank you.